So in our next section, we're going to look at the details of using BGP as the provider edge to customer edge routing protocol in MPLS Layer 3 VPN. And first, let's talk about what our current setup is from our previous example. And we'll then look at the CLI, go through some verifications, and then look at what are the specific caveats that we have with BGP as the PE to CE routing protocol. So up to this point, we have the basic L3 VPN built, where the core of the network is routers 1 through 3, as well as XR1 through XR3. And we're running an IGP, specifically we're running IS to IS in this case. And then we're also running LDP in order to establish our label switch paths between the loopbacks of the PE routers. Okay, once we had the label switch path built, then we built our VPN version 4 iBGP peerings. Specifically, we had two different route reflectors. We had router 1 and XR1, both configured as route reflectors. And then we had a full mesh of peerings from every client to both of the reflectors to both router 1 and XR1. And then we have our virtual routing and forwarding instances, our VRFs, where between router 1 and router 5, we're in VRF A. Between XR1 and 4, we're in A. Between router 3 and 7, we're in A. And then between XR1 and 8, we're in B, XR4 is in B, and router 10 is in B. And we currently have eBGP peerings set up between XR1 and router 4. Router 4 is in AS456, as well as router 5. Router 10 is in AS10. Router 7 is in AS7. And then we have peerings between XR3, XR4, XR1, and router 8. And those devices are in AS8914. So before we go into the specifics of caveats with BGP, how does the loop prevention work, or what are the ways that we can change this, let's go through a basic verification to see how are all of these pieces fitting together in the overall L3 VPN design. Now the first of this, as we saw previously, was going to be the LDP plus IGP reachability within the core of the network. So from router 1's point of view, this means that we would look at the show MPLS forwarding table, and we should see that we have labels learned for the loopbacks within our own network. So for example, for VRF-A, two of the PE routers are router 1 and router 3. This means that we have to have a label switch path that is established between the loopback interfaces of 1 and 3. And from 1's point of view, we can see that we do have a label installed, and specifically it is this label number 17. It says we're going to switch traffic out towards router 2. And if we do a trace route to 3333 and source these packets from our own loopback, we can see that we are following a label switch path. Now again, from this output where we only see a label on the first hop, that's normal in this case because the next to last hop, or again the penultimate hop, is going to be removing the topmost label before forwarding the traffic onto the exit PE. Now we'll see that when we trace through the end-to-end layer 3 VPN, we'll have a 2-label stack that ends up as a 1-label stack on the final exit PE on router 3. Router 3 is going to do the lookup on the customer route and then forward the traffic as native IP packets. So this is the normal case here, that we only see the label as we're going from router 1 to router 2, because router 2 is popping the label before it goes to the exit provider edge router, which in this case is router 3. Then likewise, if we were to go from B to B, let's say we go to router 2, and we want to trace route, do we have a label switch path to get to XR1 and XR3? So we'll trace to 11, 11, 11, 11. Source is our own loopback because that's the source of the BGP VPN v4 peering. And we should see for both of these, likewise, we have a 1-hop LSP because we're only 2 hops away from these particular provider edge routers. So we trace 13, 13, 13, source from loopback 0, and we can see that we're going over to router 3 and then up to XR3. Now the reason why, again, if we look at router 2 and look at the show IP interface brief, some of these interfaces we had shut them down, so we were not going direct to the direct peering like between router 1 and, between router 2 and XR1. Okay, otherwise, with all of the interfaces enabled on router 2, we would not see any label switch path because we are the next to last hop, both for XR1 and for XR3. Now, once we verified that we have the LSP between the loopbacks of the PE routers, next step would be our VPN version 4 peerings, where again in this case we have two different route reflectors, which are router 1 and XR1. So from router 1's point of view, if we look at the show BGP, VPN v4 unicast all summary, we could see that we have a number of peers, and most of these are within our own AS, so these are going to be our route reflector clients, and we can see that we are learning the BGP updates from the particular neighbors. Okay, if we then look at what routes are we learning, what routes are we reflecting, since router 1 is a route reflector, as is XR1, it means that we're not going to be filtering routes based on the route target value of VRFs that we don't actually own. And again, we'll come back to this in more detail when we're looking at inter-AS L3VPN, but the default behavior of VPN version 4 is that when you show BGP, VPN v4 unicast all, you typically would not be receiving VPN v4 routes that you're not actually going to install in a VRF. So from router 1's point of view, when we look at the show VRF, we currently only have VRF A configured with the route distinguisher of 1:1, which is going to be for these particular routes. But since we are a route reflector, it means that we will accept prefixes that have other route targets that we're not actually using, for example, 8888. And we can see this if we look at the show VRF detail. We can see what is our specific import-export policy is 100:100 for VRF-A, and if we show BGP VPN v4 unicast all 8888/32, we can see that this prefix does not have that target, but we are advertising it to our route reflector clients, which in this case is update group number 1. Now, once the updates ultimately get to the provider edge routers, like if we go over to XR3 and we look at from XR3, we'll say show BGP, IPv4, or show BGP VRF, IPv4 VRFB, IPv4 unicast. We can see that we are receiving these routes from our internal BGP peers, and then we should also have an eBGP peering that's going to XR4. Okay, so on XR4, let's look at the show run router BGP. So we have the peering out to 13, and then from XR3's point of view, if we show run router BGP, I think this is the, let's see, show config commit list. I need to roll back one of my configs, so let's say rollback config to L3VPN BGP. Okay, if we show run router BGP, we have this eBGP peering that's going to that CE customer. And again, if we show BGP IPv4, or show BGP VRF first, VRFB, IP4 unicast summary, we should see shortly that we have the peering up between XR 13 and 14, and then ultimately we should learn the routes. And then from the customer's point of view, like if we were to go to router 4 and simply show IP route, we see that we have some of the routes installed as BGP prefixes. Now, ultimately, when we test connectivity from the customer's point of view, we should see a 2-label stack in the MPLS core, where the topmost label is talking about the loopback of the exit PE out of the SP core, and the inner label is talking about the final destination, which is the VPN label that was generated by VPN v4 BGP. So from router 4's point of view, if we trace to 7777, source this from our own loopback, we could see that the final VPN label is not changing on a hop-by-hop basis. This should be the one that was allocated by router 3, talking about this final destination. And then 16,001, 16,002, these are going to be the transport labels that are talking about router 3's loopback. So again, unless we can do label switching between the loopbacks within the core, then the end-to-end customer traffic is not going to work over the MPLS network. So again, we will see in later sections in terms of troubleshooting what are the different things that can break this. But from a verification point of view, this would be the overall step-by-step process that we would want to go through. Okay, so next let's look at how are the specific routes being advertised through the BGP network. Now, in terms of the specific autonomous systems that we have AS 456 that is on the peering between router 4 and XR1, as well as on the peering between router 5 and router 1. Now, assuming that this is the same site for the L3VPN, what we would not want to do is to advertise the routes from router 5 to 1, have 1 advertise them over to XR1, and then XR1 advertise them back to router 4, because we could potentially cause a loop within the internal autonomous system. Now, as we talked about with regular eBGP loop prevention rules, when a route is received from an eBGP neighbor, one of the first things that we check is to see whether our own autonomous system is in the path. And in this case, when you have BGP as the PE2CE routing protocol and multiple customer sites have the same autonomous system number, the end result is that the updates are going to be dropped between those particular sites. So what I mean by this is that if we were to go over to router 1 and look at the routes that it is receiving from the internal BGP peers, if we show BGP, VPN v4, unicast for VRFA, and if we look at the route that's coming in from router 4's loopback and router 5's loopback, we can see that the autonomous system path is 456. Now, since both of these peers are in that same AS, when router 5 is going to receive those updates in, it's going to say, I'm going to have to discard that because my own autonomous system is in the path. Now, from router 1's point of view, if we look at the show BGP, VPN v4 unicast, show BGP, VPN v4 unicast, all neighbor 10.1.5.1 advertised routes, we'll see that we are reflecting, or what we should say here is, which, 10.1.5.5. So router 1 is advertising this path back to router 5, but the end result is that 5 is going to be dropping this inbound because it has its same autonomous system in the path. And where we would see this specifically from router 5's point of view is if we debug IPBGP updates and clear IPBGP star in, we should see that when we receive router 4's loopback, it says it's denied because the AS path contains our own autonomous system. So just as you would expect basic eBGP loop prevention rules, say my AS is in the path, it means I advertised it out and then somehow it looped back into me. But in our particular case here, it really depends on, are router 4 and router 5 in the same site, or are they in different sites? If they're in different sites, if they are in different sites of the VPN, we would want to make an exception for this in order to be able to advertise the prefixes back and forth between them. So what I mean by this, let's say we make a minor change to the design here, and let's move router 7 also into AS 456. Because as we saw up to this point, we do have connectivity from router 4 to router 7 when we're sourcing the traffic from our loopback, and router 7 is in the separate autonomous system. It's in AS 7. But let's go ahead and make a change here. We're going to say on router 7, this device is now going to be in AS 456, so let's say show run router BGP, and we will say under BGP 7, for this particular neighbor, we'll say that the local AS is 456. So in other words, we're advertising to router 3 that our autonomous system is not number 7, our autonomous system is 456. Okay, then from router 3's point of view, we're going to change the remote autonomous system for this particular neighbor. If we show run section BGP, we're going to say that under router BGP 1, this neighbor is not in AS 7, this neighbor is going to be in AS 456. Okay, if we then look at the show BGP, VPN v4, unicast all summary, we see that we now have appearing to router 7, we move their AS to 456, and if we show BGP, VPN v4, unicast all, we should see that when we're receiving the updates in from 7, notice that it has 456 as its own autonomous system. Now again, what this is now going to mean is that when we look at the advertisements that are going from either XR1 to router 4 or from router 1 to router 5, when those get advertised to the eBGP neighbors, router 4 and router 5 are going to be dropping this inbound because their own AS number is in the path. Now you'll see that this works a little bit differently on regular iOS versus XR. And what I mean by this is that from router 1's point of view, if we look at the show IP BGP neighbor advertised routes, we should see that we are advertising that path to them. So now it contains 456, but from router 5's point of view, we're going to be dropping this as the update comes inbound because our autonomous system is in the path. And from XR1's point of view, if we likewise look at the show BGP, VRFA, IPv4 unicast neighbor, 10.4, so this neighbor is 10.4.11.4 advertised routes. We see in this case, we're actually not advertising them anything. So from router 4, if we look at the show IP BGP summary, we can see we're receiving 0 routes from 11. If we were to debug IP BGP updates and clear IP BGP star in, we can see that from router 4's point of view, it's not learning anything from XR1. Now, ultimately, the end result is the same, is that they're not going to be able to install the routes in the table because of the autonomous system number in the path. But the difference is that iOS XR implements this as an outbound filter, where iOS implements it as an inbound filter. So you could say that the XR implementation is a little bit more efficient here because it looks at the path and it says, well, 456 is already in the path to begin with, so there's no reason for me to advertise it to this neighbor because I know that they're just going to drop that update in. So as an optimization to this, it says, well, I'm just not going to advertise it anyways, and I'm going to save myself some updating, some CPU cycles in terms of the control plane. But from router 1's point of view, it is advertising the routes to 5, and then these are getting dropped inbound. And the reason that this is significant to note here is that the solutions for allowing these routes inbound are going to be different between regular iOS and iOS XR. Now, the one that is specific to MPLS VPN would be to say that when I advertise the route outbound to this particular neighbor, I don't want to include their AS number in the path. What instead I'm going to do is basically delete their AS number and replace it with my own. And in this case, router 1 and XR1 there in AS1. So we're going to take 456, replace it with 1, and this is what we call the AS override feature. So AS override is going to be configured under the BGP process, under the VRF, under that particular neighbor, and then under the address family for IPv4 unicast. So from XR1's point of view, when we look at the show round router BGP, specifically that config would be going under here where we have the route policy applied to the neighbor. So let's go to the global process here. We have router BGP1. In VRFB, we have that particular neighbor, that particular address family. Actually, it is this neighbor. Okay, VRFA, that particular neighbor and address family, and we'll say we want to do an AS override. So override the matching AS number when sending the updates. Okay, if we show config, again, this is placed under the VRF, under the neighbor, and the AFI. We'll go ahead and commit the change. And if we now look at this from router 4's point of view, if router 4 were to ask for an update inbound, we could see now we're receiving the updates about router 5's loopback and 7's loopback. And if we look at this in terms of the AS path information, we can see that we've taken AS 456 and we replaced it with AS1. So we're overriding their autonomous system number with our own AS. But notice here that it did not edit the other numbers in the path, where from router 7's point of view, since we were doing the local AS config, router 7 is prepending 456 onto its own update, where specifically we had router 7 configured in AS7 globally, but then we said to this neighbor the local AS was 456. So this means that from router 3's point of view, when we're receiving that update in from router 7, we have both the local autonomous system and the global autonomous system. So it doesn't actually replace the autonomous system, it's just prepending the number onto it. And you can configure it to not do this, but this is unrelated to MPLS. This is just related to basic BGP AS path prepending. So from router 7's point of view, if we were to show run section BGP, we could say that when we apply the local autonomous system onto this particular neighbor, we don't want to prepend our own AS, and we want to replace the real AS with the local AS in the BGP update. So let's say replace AS. Okay, if we now look at this from router 3's point of view, we should see that for the loopback of 7, we see this as if it is coming just from 456. But the default behavior, as somebody had mentioned here, with the local AS is that by default, you're going to leave their global AS in there, and then you're going to prepend the local autonomous system number. So it really depends on what is the number that you're specifically trying to override. If the remote AS was 7, then that would be replaced with 1. In this case, it was 456, so 456 is being replaced with 1 on the other end. So now from router 4's point of view and from router 5's point of view, we should be receiving the, actually not from router 5's point of view because we didn't configure that yet, but XR1 is now overriding 456 with AS1, and we could then send the update outbound to them.